In this example, we're going to be sketching the graph of this fifth degree polynomial, and we're going to make sure that we are showing the correct behavior at the zeros as well as the correct end behavior. So let's first analyze behavior at zeros. So we'll go from here. Zeros. To get the zeros, we need to look at the factors. So when we're looking at the factors, we've got the factor x cubed out front. We do see this in the factored form that's given. Now that negative that's out front is really just the leading coefficient, and so I'm not going to worry about that as part of the factor. It's the x cubed that I care about. We also have the factor x plus 2, and we've got the factor x minus 3. Okay? Each of those factors gives us a 0. So the zeros that come from these factors are by setting the factor equal to 0 and solving. So we've got the x cubed equal to 0. We could cube root each side and we'd still just have x is equal to 0. For the next one, x plus 2, subtract 2 from both sides, and that gives us x equals negative 2. And then the x plus 3 gives us x equals 3. So we've got 3 zeros that we could go ahead and graph here. So we've got the 0 at x equals 0, so that's at the origin. We have the x value of negative 2 that has a 0. And we've got the x value of 3 that has a 0. So we are going ahead and plotting those points, knowing that the graph either touches or crosses the x-axis there. And so next we want to figure out what is happening at those particular zeros. So we need to look at multiplicity. So multiplicity, when we're looking at that, we're looking at the power the factor has. So x cubed, that power of 3, is telling us that the factor x has multiplicity 3. The x plus 2 doesn't have a power specified there written in, so it's understood to be power of 1. And the same thing happens for x minus 3. So we have multiplicity 1 on each one of those. So the multiplicity gives us the behavior, which is what we're really in search of. So behavior. Okay. Each one of these multiplicities is odd. So we know that each one we're going to have the graph crosses. But there's a difference between what a crossing looks like when the multiplicity is 1 versus a higher odd multiplicity like 3. When we have a higher odd multiplicity, not only does it cross, but it also flattens. So that gives us the behavior at our 3 zeros. And the last thing we need to analyze is the end behavior. So the end behavior and the behavior at zeros work together to give us a nice graph. So our end behavior, we start with the dominating term. That dominating term is the term that has the highest power. It's not necessarily the term that appears first in some random writing of f of x, but it really is the term that has the highest power. So in our expanded polynomial, we see the highest power on x is 5, so it's the term negative x to the 5th that would be our dominating term. And we do have to keep that negative and any coefficient that comes with the highest power of x. Now, if we were not given the expanded form, but rather if we only had the factored form, I want to show you how to get that dominating term. What we do is we keep the leading coefficient as well as any of the x powers that go in any factor. The highest power of x, we'll say, that goes in any factor. So we're keeping all of those x's, but we're dropping the lower power terms, which would be those plus the constants in the last 2 factors. And so to get that dominating term, we multiply that first factor, negative x to the 3rd, times just x to the first power there. We're dropping the plus 2 part, and then times x again, just to the first power, because we are dropping the minus 3 part. And so when we multiply those terms together, we see that we've got the negative out front as our leading coefficient, but then we have x's as the base for all of them, and so what we do is we add the exponents. So we have 3 plus 1 plus 1 would give us that power of 5 that we were expecting, negative x to the 5th, that's our dominating term. Now, the 2 things that we need to observe about this dominating term have to do with the leading coefficient and the highest power that we actually have. And so the leading coefficient, the observation we're making is that that leading coefficient is negative, and for the highest power, the observation we're making is that it's odd. 5 is an odd power. And so the odd power is telling us that the arrows are going in the opposite direction, odd opposite. You can also think about the graphs of the line y equals x, or even the curve y equals x cubed. Those end arrows go in opposite directions. And so that is telling us that our two arrows are going in the opposite direction. But then the negative for the leading coefficient is telling us, well, are we going in the opposite direction but kind of sloped upward or downward? The negative says slope downward. So just like a line with a negative slope, we would have the sloped downward end arrows. And so that would be our end behavior. So what we do to get our good graph is go ahead and plot, just like we did for the zeros, we're going to plot our end arrows. And so we're going to start from the left to the right, start at our leftmost arrow, and go to our first zero that we come to and make sure we do the right thing there. So each one of these we're supposed to be crossing, but only at x equals 0 do we have to flatten also. So moving from the left to the right, we just directly cross at -2, but then as we bump back up here for the 0 that's happening at x equals 0, we got to have a bit of a flattening going on. And then we come back down here to the 0 at x equals 3, and we just cross very directly. Notice that again, I come to the end arrow that I expected, so that my zeros are working with my behavior at the ends as well. And so if it ever doesn't come together correctly, then something's wrong. Either you've messed up one of the behaviors of the zeros, or missed a 0 possibly, or you've messed up the end behavior, because these things should work together to put together a graph that makes sense.